Hello, welcome again. We are covering the topic centrifugal compressor for civil services main IFS and Gate Aerospace exam. Now we will solve one question based on this topic from IAS 2025. The question is: a centrifugal compressor is to be designed for an industrial application handling air. The inlet temperature conditions are P01 is equal to 1.1 bar and P01 is equal to 295 Kelvin. The air enters the impeller actually without any pre-burn. The axial velocity is uniform throughout the eye and is equal to 143 meter per second. The eye tip and root diameter are 0.3 meter and 0.15 meter respectively. Calculate the mass flow rate of air. The overall diameter of the impeller is 0.5 meter. The power input factor is 1.04 and slip factor is 0.9. The rotational speed of the compressor is 290 revolution per second. The isentropic efficiency of the compressor based on total head is 0.78. The radial velocity at the impeller tip is 143 meter per second. Assume that half of the total losses occur in the impeller. Determine the pressure ratio and the power required to drive the compressor. Also determine the axial depth of the impeller channel at the periphery of the impeller. Draw TS diagram showing the variation of both static and stagnation pressure and temperature in the impeller and the diffuser. For air, gamma is equal to 1.4, Cp is equal to 1.005 kilojoule per kilogram per degree Kelvin. So this is your schematic diagram of centrifugal compressor. This is your impeller eye. This part is your impeller, and this is the rotating part, and second part is your diffuser. So here the air is sucked, and we will take we will represent the condition here by suffix 1, and here the air leaves the impeller. We will represent the condition of air by suffix 2, and here the air leaves the diffuser or whole compressor, and here we will represent the condition by suffix 3. So here in the question, initial stagnation pressure and stagnation temperature are given. So stagnation pressure is 1.1 bar and stagnation temperature is 295 Kelvin, and it is given that the velocity is axial and inlet velocity is axial. So there is only one component of velocity of air, that is CA1. So that is 143 meter per second, and that is equal to absolute velocity. So this is the inlet velocity diagram that we have studied. Okay, so this is your axial velocity and this is your CA1, and this is the speed of the blade at a particular radius in the impeller eye, and this is relative velocity component. Okay, so this is your inlet velocity diagram. Now initial stagnation temperature is given, static temperature we have to find out, and this velocity is given. So from the total energy condition we can find out static temperature. So that is your total energy, Cp into P01, and this is your thermal energy, this is your kinetic energy, original mass. So now we have all the values except T1, we can find out T1. So T1 will come out as 284.82 Kelvin. So now we have found out the static temperature. Now to find out static pressure, we will use isentropic formula. So that is P01 by P1 is equal to T01 by T1, therefore gamma by gamma. Gamma is 1.4, gamma minus 1 is 0.4, and this T01 is 295 and T1 is 282 and P01 is 1.1. So from this we get P1 as 0.97277 bar. Okay. So now we have P1, we have T1. So using state equation we can find out density at inlet output. So that comes as 1.190 kilogram per meter cube. Okay. Putting the value of P1 and P1. And now density is known, and initial velocity is axial, and that is also known. And this area where the air is entering is this part. Okay. So this is your eye root, and this is your eye tip, and area is your 5/4 eye tips square diameter minus eye root square diameter. Okay. So it will come out as 0.053 meters square. Okay. So mass flow rate will be this is density, this is area, this is velocity, so that will be 9.01 kilogram per second. Okay, so that is your mass flow rate. So that is the answer to first question. So now for the next part, this is your impeller T, and its diameter is 0.5, and its speed is 290 revolution per second. Okay. So 290 revolution per second, so that is revolution. So actual speed is pi dn, that is 455.5 meter per second. Pi d, and d is your 0.5 meter. Okay. And now we'll find out the stagnation temperature rise. So that is your work done in terms of power input factor, slip factor, u. So that we have find out power input factor is 1.04, slip factor is 0.9. So this work done will be converted into heat energy. So heat energy is your Cp T03 by T01, and Cp is your 1005. So that is your temperature rise. So it will come out as 193 Kelvin, and initial stagnation temperature is your 295. So the final stagnation temperature at the exit of the diffuser will come out as 488 Kelvin. Okay. So now this is the actual temperature rise. So now if we assume that the process is isentropic, then isentropic temperature rise will be your T03 dash minus T01. So that will be calculated by multiplying this temperature rise with efficiency. So it will give T03 dash minus T01. Putting the value of T01, we can find out T03 dash. So T03 dash is the isentropic temperature attained after compression, if the compression is isentropic. Okay. So now as this temperature is isentropic be achieved, so we can apply isentropic relation also. So T03 dash by T01 is equal to T03 by T01, here gamma by gamma maximum. Okay. So T03 dash is known, T01 is known, so pressure ratio comes out as 4.23. Okay. So this is your overall pressure ratio. So now it is given that the velocity is radial, and that velocity is equal to axial velocity. Okay, given the radial velocity at the impeller tip is 143 meter per second, so CR2 is your 143 meter per second. Okay. So 143, and this outlet diagram of this centrifugal compressor is like that. So this is your radial velocity CR2. Okay. And this is your 143 meter per second. This is your radial velocity, and this is your tangential velocity, and tangential velocity will come out as sigma into u. Okay. So that will come out as 410. So u is 455.5 and sigma is 0.9. So from this, this is radial and this is tangential. So the total velocity will be, or total velocity square will be CR2 square plus CW2 square, that will be 143 square plus 410 square. Okay. So now the dynamic temperature at the exit of the impeller will be C2 square by 2Cp. So that will come out as 93.8. Okay. So now after this we will go in the next video.